Okay, we've seen that if we have observation error, something along the lines of y is equal to ax plus e, that it's possible that a straight up solution can amplify that error. And in fact, depending on how e is pointed, we could get all the way up to a worst case scenario of our reconstruction squared could come all the way up to 1 over lambda n squared, where lambda n, of course, is our smallest eigenvalue, so 1 over lambda n would be the largest. On the other end of the spectrum, pun intended, we have 1 over lambda 1 squared. And so this is our best case error, and this would be our worst case error. So that comes out, it's a pretty straightforward thing to do, and we kind of went through how to see that previously. Now, what happens, what is our average reconstruction error, and how do we get that? So, for our average reconstruction error, we're going to have to make some assumptions, and in this case, we will assume that the entries, the individual samples in our vector E, are random, identically distributed Gaussian. So let's write this down. We will assume that random, independent, identically distributed Gaussian, where EI is normal, a mean of 0, standard deviation of sigma, I equals 1 to n. So all of that implies that E expected value of our I'm mixing notations, EI EJ, let's do that, equal sigma squared for I equals j, and 0 for I not equal to j. Okay, so now we've got our setup here. How realistic is this? Well, I don't know. It may not be very realistic for some applications, but others it may be a good fit. But it still gives us some intuition for what's going on. So we want to find the expected value of E squared. And that's the expected value, sum over n of En squared. Which is equal to the expected value, no, actually, it's equal to the sum of the expected values of the individual elements squared. And the expected value of these squared, since we're a zero mean process, is just going to be sigma squared or n sigma squared. So there we go. But that doesn't tell us anything about what happens when we actually put it, we find our reconstruction error. That's just the expected value of the norm squared of E. So we're going to repeat this process, and this time it'll be a little bit more involved, but we're going to have norm squared of A inverse times E. And what we're going to do to actually make this computable is do our spectral decomposition of A and write this out in terms of the inner product that induces that norm. So we could write this as V lambda inverse V transpose E transpose V lambda inverse V transpose E and this becomes E transpose V lambda inverse V transpose V lambda inverse V transpose times E. Well, these two values here cancel because V transpose is equal to V inverse. So now we can express this in a couple different ways, and one of those is simply to say this is equal to lambda inverse V transpose E with lambda inverse V transpose E, because we've gotten rid of the other V in there. So this can be written again as a sum, and this technique is actually pretty common for some of these proofs, because once we simplify it down a little bit, so we've got the magnitude squared using the spectral decomposition, and we just push it through, terms disappear, and we end up getting something we can actually use. Now, following tradition, we've got an expectation and a sum, so let's swap the order, and now we get a sum of an expectation. Oops, that should be little n squared times the expectation of absolute value of E inner product with Vn squared so what's this going to be? Well, we need to do a little bit of analysis. It turns out this is going to be pretty simple, but let's push through and see what that is. So the inner product of E with V is going to be something like this. it's going to be the sum from m equals 1 to n of Vn, and I'm going to put brackets to indicate the mth sample of that vector, times Em, the mth sample of that vector, and that's squared. So that's going to be the sum. Go m equals 1 to n, L equals 1 to n of V n m E m V n L E L. And remember, this is all inside the expectation. So our eigenvectors aren't random. So if we take this quantity then and throw it back inside an expectation, that's just going to be the double sum over m and L, Vn m Vn L, times the expected value of E m E L. But that expectation is 0 unless m equals L. So the whole expression then is just equal to a single sum, one of them collapsed, of V n m squared sigma squared. Okay, so inserting that back up above, we get n times sigma squared times 1 over n sum of 1 over lambda n squared. And so this is the average of the eigenvalues squared. Let's write it this way, is equal to sigma squared, the n's cancel, times n equals 1 to n of 1 over lambda n squared. So we took the variance that we had before, and that makes sense. That was part of E. And we now have essentially the average, or the, I guess now that we've multiplied it by n times sigma squared, which is what E was, the norm of E, times 1 over lambda n squared. So that's our average reconstruction error. Let's put all this together in one spot. See what we've learned so far. That is, we create an observation where we have y is equal to ax plus e, and this is our unknown quantity, this is our error. This is our known observation matrix. And X is, of course, our observation. And we assumed, for now, that A is symmetric, or, if appropriate, Hermitian. And positive definite. If that's the case, if we have a positive definite matrix and it's symmetric, we will have an inverse. So we can reconstruct or estimate, depending on how you view this, x tilde is equal to A inverse y, which is equal to x, yay, plus A inverse E. And then we have our best and our worst case reconstruction, errors here. Reconstruction or estimate error is determined by our eigenvalues, and it all depends on the direction that E is pointing. So if E is pointing in the direction of Vn, then we're going to have our maximum error. That'll be equality. And if it's pointing in the direction of E or V1, then we're going to have our minimum reconstruction error. And then finally, we'll have our average reconstruction error. And we had to assume that our EI, or normal sigma squared, and IID, and we had the expectation of x tilde minus x squared is equal to sigma squared times the sum 1 over lambda squared n. So that's the easy case, the case where we actually have a symmetric positive definite A. What does that mean in terms of a real problem? That means that we have exactly as many observations as we have variables that we're trying to observe. And it also tells us that the observations are independent. In other words, each observation is giving us some new information. So those are two things that are required to have this positive definite nature, something that is not something that gives us an A that's invertible. We're going to look at next time. We'll spend a little bit more time looking at what happens when we suddenly have too many or too few observations. So see you then.